Algebra 1, Section 5.3, Function Rules, Tables, and Graphs. You will need graph paper for this section. I have on my notes here 2 full sheets of graph paper, meaning two-sided sheets. You might want to practice along with me on this. If you choose not to, I think you might still need 2 sheets by the time we do all the graphs that it takes in this section. Hopefully I've reminded you of that when we get to this far, but if not, as always, there's graph paper available in my room. You might want to just always have a few extra sheets on you. It's also available for download, at least one-sided ones, so you probably have to print 3 or 4 of them from Google Classroom. All right, so Section 5.3, there are 3 popular ways in Algebra 1 to model a function. Those three ways would be a function rule, a table, and a graph. And I'm going to make sure that I'm going to make these so that they are all related. So I have an example of a function rule, y equals -1/2 x plus 1. We know that that's going to yield a line. And the second popular would be a table. And when we do a table, as you've already seen and as you're going to practice a lot in this section, you pick the x values and then we get the corresponding y values. Okay, so as I plug -4 in for x, again, I'm just going to do the same thing for all 3. So these are all different representations of the same function. When I plug -4 in here, -4 times 1/2 would be +2, plus 1 would be 3. When I plug 0 in, I really like to plug 0 in. It's a nice way to get an easy point because it makes this whole thing 0, and then you're left with just that plus 1 there, so 0, 1. And then let's plug in 2. I just picked these points at random, -4, 0, and 2, these x values. Anyway, 2 times -1/2 would be -1 plus 1 would be 0. So there's 3 points that we can plot, -4, 3, 0, 1, and 2, 0. Now, the reason that I would do 3 points, or I should say at least 3 points, is that because I'm expecting a line because of the form of this and how many times we've seen something like this. We'll formalize that in the next chapter, but we've seen enough of this, I think, to just expect that it's going to be a line. When I put 3 points on the graph and they actually do form a line, I ought to feel pretty good that what I'm about to put on the graph is accurate. Okay, so here's a line that passes through all of those points. Do please draw long, straight lines. Use a straight edge if you would. I guess I would just really prefer you to use a straight edge, even if you're good at drawing straight lines. And they should span the graph. Go from one end to the other, as you see my graph doing there. Don't draw something short. Draw something long, at least so that you can see where it crosses the x and y axes, if at all possible. Okay. Now, question about that. What if instead of saying y equals -1/2 x plus 1, I would have said f of x equals -1/2 plus 1? What's the difference? I think I didn't say, I didn't finish when I was preparing for this. I didn't say the conclusion. How would f of x equals -1/2 x plus 1 differ from these? Is what I meant to say there. And the answer is they wouldn't. This is the same thing as this. Don't be confused by f of x notation. F of x means y. It's just the dependent variable. But what it does afford us is that when we plug in -4, if we wanted to model that this way, which our book often does, you can show that you're plugging in -4 for x here and in the calculation, in the expression, right? Plug in 0, it's f of 0 is -1/2 times 0 plus 1, etc. Okay? So with that, let's do an example. Here's an example that says at a local video store, you can rent a video game for $3. Now, if you were in class, we'd have a good laugh about this because these video stores hardly even exist anymore. Are there any left? But when I was growing up, you could rent videos at a video store, and then when I was in my early adult, I guess, or maybe even late teens, they started renting video game systems and video games, and that's what they're referring to here. It costs you $5 a month to operate your video game player. The total monthly cost, C of V, okay, so there's your function notation again, C of V, that just means the output, the dependent variable. It depends on the number of video games V you rent. Use the function rule C of V equals 5 plus 3V to make a table of values and a graph. Now again, This ought to make perfect sense to us based on the explanation given. The cost is $5 no matter what, plus 3 more for every video game you rent. Okay, I rent one video game, that's going to be $8 because 1 times 3 is 3 plus 5 is 8. I rent 2 video games, that's going to be $11 because 6 plus 5 is 11. Okay, and let's go ahead and start with just those two values. In fact, those that I just outlined, V and C of V, in a table. And let's go with 0, 1, 2, 3, 4. I said 1 would give you 8, 2 would give you 11, 3 would give you 14, right? 9 plus 5 is 14. 4 would give you 17. In fact, 0, if I go backwards here, would be 5. If you have this program or this deal, you're going to pay $5 no matter what. And then if you rent one game, you're going to pay 8 and on up. Now, with that in mind, maybe it'd be smarter to go by, I don't know, 2s or 4s or something. I'll go by 2s. 2, 4, 6, 8, 10, just to show a little bit more of the graph of this, right? We can still go by 1s this way because we went by 1s in our column here. And to graph those points, 0, 5 would be here, 1, 8 here, 2, 11, 3, 14, 4, 17, and then you know what, 5 would give you 20. Okay, now here's the thing, and this is new. What we've taught you so far is, hey, get some points on there so that you can see what the shape of the thing's going to be, and then go ahead and draw yourself a line that connects all the points. And that would be fine if I just said, hey, graph the function C of V equals 5 plus 3V, and you had no context about the video games. But you know what? Last time I checked, you couldn't rent half a video game. You couldn't go in and say, well, I only have $6.50 to give this month, so can I have half a video game? So to draw a line here would suggest that it's a continuous function, that they're in the video game example, that there are possibilities between these 2 points. Now here's what the book does. The book will connect them with a dashed line. And I'm not totally against the dashed line, but I rather say that you just do this. Put point here, point here, point here, point here, and point here. This is what's known as discrete. I don't know if you saw on the previous slide, I'll go back to it, but we've got continuous versus discrete. Continuous would mean, yes, if I just draw a line in here, like I don't have to pick up my pencil at all, I can just draw right through here, and that would be continuous. This is discrete. This is the other way that you can model a function. And because they did give us the context of the video game rentals, the store rental, I'm going to leave it just like this. Okay. Now, it would be implied that the points would continue. You know, there'd be another one here, and there'd be another one off the screen, etc. The more video games you rent. Okay. This is what's known as discrete. In fact, let's go back to that now. Continuous and discrete. So continuous would be everything else that we've dealt with that you don't have to pick up your pencil and make a bunch of points. So continuous would just be a line that does this, or continuous would be an absolute value function that does something like this. Parabolas, I think we've seen very briefly. These are all continuous because I can just go like that and draw, right? These are continuous. Whereas discrete is more like a scatter plot. And it still can be a parabola. It still could be a absolute value function, right? It's likely to be a line though, and I'm just freehand drawing here, you understand, right? These are considered discrete, continuous versus discrete. The word discrete is probably new to you. The word continuous ought not be, right? Continuous meaning you never pick up your pencil to place it down somewhere else or to make points like that. All right. All right, next example. It says at a ball game, they charge $2 for a hot dog. The function C of H equals 2H describes the cost of H hot dogs. Use the points for each input value. Connect the points with a dashed line. Again, I don't think we need to do this. You don't buy partial hot dogs, so we're just going to put the points down where there are whole hot dogs and what you paid for them. Each of these last 2 examples would have been okay had we just zoomed in on the first quadrant here. I have graph paper for that too. I just didn't set it up for this example for this lesson because we can do it without it, but you sure could. And one other thing, they really didn't need to give us the function in either of these two examples that are real life discrete examples. If it's $2 a hot dog, well, hey, its cost is equal to twice or 2 times h, and that's what they're showing here. Okay. So what if you bought? Let's not even do a t-chart this time. What if you bought 0 hot dogs? How much money would you spend on hot dogs if you bought 0 hot dogs? $0. If you bought 1 hot dog, you would spend $2. If you bought 2 hot dogs, you would spend $4. 3 hot dogs, 6. 4, 8. 5, 10. And to me, that says done, right? You're not going to buy negative hot dogs, so you're not into the second, third, or fourth quadrant. And yes, it would be implied that it would continue in this way, but this is a discrete function with each one of those points. Next time you're at a ball game, go up and ask if you can buy a half a hot dog. I'm pretty sure the answer is no. All right, and then the last example, 2 parts to the last example, but the last example says graph the function y equals the absolute value of x plus 2. Now, notice I kind of paused there when I said absolute value of x plus 2 because the plus 2 is outside of the absolute value. And again, we're going to make a t-chart here. Notice there's no context to this problem. There's not some real situation that we have to consider. So we're just going to graph this whole thing, and this will be continuous. Okay, so what if I plug in 0? 0, absolute value of 0 plus 2 would be 2. What if I plugged in 1? That would give me 3. But what if I plugged in negative 1? Negative 1's absolute value is 1, plus 2 would be 3. So right away, because you have this, you know that this is your vertex here. There's a vertex at 0, 2. We have a point at 1, 3, and a point at negative 1, 3. You know what's going to happen when you plug in 2 and negative 2? You're going to get 4. And you can probably see from there what this graph is going to do. Let's make it blue. That looks good, right? Again, a graph that covers as much of the coordinate plane as I can get it to. And then one more. Let's see, what are we going to do here? We're going to plug in 0. I'll just start at 0 again. 0 squared is 0 plus 2 is 2. If I plug in 1, I'm going to get 1 squared is 1 plus 2 would be 3. If I plug in negative 1, think about that. Negative 1 in parentheses squared. This is like saying f of negative 1 is equal to the quantity negative 1 squared plus 2. That would be 1. We already talked about that in class. 1 plus 2, that's 3. And then away we go, right? Again, you found the vertex because of this. 2 squared is 4 plus 2 would be 6. Negative 2 would also give you 6. So we have this. Just for good measure, let's throw a 3 in there and see what we get. 11. So 11 will be just off my window here, but I can still reach it. There we go. Now, this is not a dot to dot. This is not a line segment, line segment, line segment. Try to do yourself a favor and draw a curve. I am not an art teacher. I don't need it to be perfect. Drawing on this screen that I have here is far less than perfect. So we're looking for something that's ballpark correct, but it is absolutely a curve, and not a series of line segments. Okay? All right, that is all. Thanks for watching.